Thank you, Ulla, and thank you for inviting me here. It's really a pleasure to be here and tell you about this high-throughput screening and toxicogenomics, which is a handful actually to present, but I will try my best and let's see where we get. So I'm an assistant professor at the Institute of Environmental Medicine at Karolinska in Sweden. And yeah, I'll try to get you through some high throughput screening and toxicogenomics and see where we might be headed with regards to actually using nanomaterials in products. So let's see. Okay. So, so just an overview. This is a picture that was published already a long time ago when the EPA came out, or the National Research Council in the US came out with their new view of a 21st century toxicology, basically. And it's all about transforming toxicology from an observational to more of a predictive approach where we would avoid animals, as we all know. And so this builds largely on systems biology. And of course, that entails critical toxicity pathways and computational modeling of those pathways. And what I want to point out here specifically is that much of what you heard just from Julia, Ulla, and Anne is information and data that we use in order to identify the most predictive key events and toxicity pathways and molecular players that are actually predictive through modeling approaches of the final outcome in human. And of course, they also prioritize for the worst case where you do have to use animals. We of course hope that we could actually avoid that quite a lot, and this arrow would be quite thin. And when it comes to nanomaterials, of course, we do of course normally have epidemiological information, like you've heard from all of the previous speakers regarding asbestos and other types of known particles. And that data is of course also useful for the actual identification of predictive pathways. So, and when you have these predictive pathways, you can apply them in high throughput manner and also in first tier testing systems or testing strategies, which I will try to make a point of. So, and then leading you towards more complex systems if necessary. And whether it's animals or more complex in vitro systems is another debate. So let's see if I can get forward. So, and as you know, nanomaterials, you've heard this over and over again from the previous speakers. Nanomaterials are complex. They come in many, many different forms, nanoforms. They have maybe similarities, but we don't really know, still don't really know what is actually predictive of the final toxicity. And so high throughput screening really has become very important. I mean, it's important on the chemical side as well, but nanomaterials have really struggled with this difficulty in identifying predictive physicochemical characteristics. So high throughput screening is really something needed within the field. And there has been a strong focus on trying to implement these methods. So, and some of these are shown from the efforts of actually developing grouping and read-across approaches, which go all the way from materials, physicochemical activities and their surface activities and shapes and stuff like that, all the way to the very early biological effects and the so-called bio-nano effects as a first start. And in addition, safe by design strategies have also had a strong role in the development due to the fact that we really want to make a more sustainable world. And you heard, I'm happy that the previous speakers talked about safe by design, because this is also a point that I'm going to make, where omics and high throughput screening and adverse outcome pathways, I will talk a little bit about that as well, do play a large role in really enabling safe by design, where you really take, you really actually perform a type of pre-regulatory risk assessment already during the actual innovation of nano-enabled products or nanomaterials themselves. So, and in fact, the NanoReg 2 project recently extended the original recommendation or requirements of parameters needed for grouping of nanomaterials, which you see here on the left, the ECA key physicochemical parameters, which do go all the way to biological reactivity and photoreactivity. And in the project, and these build on the what they are, where they go, and what they do concept that was developed within nano projects over the past years. And NanoReg 2 then extended these parameters slightly to include specifically a lot more physicochemical characteristics, a lot more bio-nano characteristics, but also importantly for the high throughput screening that I'm going to focus on, also a lot more parameters for human toxicity, which really, it looks like there's 4 here, but actually entails more, because all of these, as you've seen, genotoxicity, for example, requires more than just one assay and one endpoint assessment. So high throughput screening really supports this advancement towards incorporating high throughput grouping approaches of nanomaterials. So, okay, so this is an overview, an example basically of a tiered data-driven workflow, which follows in the lines of the TOX21, the 21st century toxicology, where you see a type of screening of many. So you start off here at the very left with a screening of a lot of nanomaterials. You can include chemicals as positive controls, or also, of course, positive nanomaterials are valuable, as Julia mentioned, for example, and at multiple concentrations. And I really mean more than 3, which is often the traditional number of concentrations included, or even 6, but we really use a lot more, and I'll show you in a bit how it looks. And this first step then takes you through assessment of very basic cellular toxicity endpoints, where you assess the very initial activity doses, or doses that show activity. And you might include cell viability. You might go further and have proliferation and other types of apoptosis, reactive oxygen species. Often it's a strong focus on cell viability, including many different types of mechanisms. And then you go to a next step where you deepen this analysis. You might include equally many nanomaterials as you had in the previous step, but here you start concentrating on specific doses that show activity here, or that don't show activity, actually, the doses that are subtoxic. So you might want to, if you're thinking about genotoxicity, you might actually want to focus in on the doses that are have very low toxicity, because you don't want to see toxicity or cell death related genotoxicity, but rather particle specific genotoxicity. So, but you can also screen with these immunochemical staining arrays. You can screen a multitude of different endpoints with immuno staining, and including predictive biomarkers, really, of that we've learned over the years are associated with adverse outcome. And then finally, you get into a step that we currently see as the toxicogenomic profiling of the selected few. Now, I will get back to this also because technology is developing, and toxicogenomics is not only low throughput anymore, but has become higher throughput in terms of number of samples. So many see toxicogenomics as a high throughput method, but in fact, it is a high content method where you screen few samples, selected nanomaterials at selected concentrations based on these earlier steps, and you then assess molecular pathways and gene expression changes in these samples. But this is, as said, becoming higher throughput equally to these other steps. So there are differences or new things happening also there. And I will get into that in a bit. So, so if you then look at the first steps, the first two steps actually that I showed, this is a typical screening approach that we have taken over the past years, where we screen for a number of different endpoints, which are related to a number of different mechanisms. We screen them at very many time points, in this case, 3 in most of them, but at some of these I think are actually screened. The apoptosis one is actually screened at up to 10 or 15 time points. Here I've included only 3. And we screen at both with serum and without serum. And this matters in terms of the toxicity of the nanoparticles, and also, so it matters because it has a coating effect on the nanomaterials. So, and we use 12 concentrations. We can have more than that as well. And often 4 replicates, preferably even more than that. We sometimes look at 6 replicates, which means that in the end, we come up to 30,000 endpoints that need to be analyzed. And this is, of course, a challenge to actually analyze and present this data. And normally what it looks like when we've done this is you get these heat maps where you have different conditions. So if you look at, these are 2 boxes showing without serum and with serum, and you can see that without serum, there's a slightly higher toxicity due to the fact that the serum coats the materials and makes them less reactive. So, but you can see then the different endpoints that were measured here. Here you see actually all the different time points for apoptosis, all the different doses at all the different time points, and you have a mess actually of parameters that need to be considered in different types of modelings. So this is a challenge at the moment, and we're working quite a lot to figure out how to present and how to incorporate this type of data in different risk assessment processes. And I will try to make a point out of that in a moment. So, so how do we then use this data? We have started off with using scoring concepts. So the EPA has developed a method or a tool actually called the Toxicological Priority Prioritization Index, or the ToxPi. And it actually provides you with these pies, which have pie slices of different sizes depending on the activity and the weight of that specific endpoint in an overall final score. So this is a complex concept of how we really integrate all of this, but it considers the dose responses from all the different time points and from all the different conditions that have been assessed with and without serum, for example, and integrates this into one pie slice so that each pie slice then represents one of the endpoints that have been measured. And what you can then do is to get a pie for each material that has been tested. And that pie is a basis for assessing similarity in toxicity between these materials, which means that you can also cluster or hierarchically cluster these materials based on their toxicological response. In this case, in only one cell type. It can be included in many different cell types and so on. So the complexity can increase, and also the visualization can change depending on how much information you actually include in these. But it's a transparent way of showing data integration. And what I mean with transparent is that you can, the overall scoring of this data means that you get a final score that can be used for ranking. So you can use this overall score for just a simple ranking from the most toxic, in this case, 2 chemical positive control chemicals, and the nanomaterials come after, to the least toxic. And that means that you can already begin taking decisions in, for example, safer by design approaches. And what that means is that the lowest toxicity, of course, assuming that this is covering all the toxicity that you would assume the end product to be involved in, you can start prioritizing these first materials for actual incorporation in the innovation process, while the last most toxic materials might need further testing in tiered strategies where you deepen the analysis, for example, towards genotoxicity assays, such as the ones described by Julia. So this is the concept behind, or the challenges and the proposed solutions, basically, to actually incorporate this type of data in risk assessment. So turning to the last, back to the slide that I showed before, those two, those results that I showed previously basically covered this type of high throughput screening where you have a first tier or a first step screening, which gives you selected doses that are low toxicity or subtoxicity, whatever you want to call it, and you screen for further key events or molecular players that matter. And then turning to this last toxicogenomic step or tier, if you want. Nowadays, as I said, this type of methodology is also getting more high throughput. So it used to be focused on quite few samples, so that you would have few nanomaterials and only few doses and few conditions. But during the past 10 years, I would say the omics technologies, and in particular transcriptomics technologies, which are called high throughput transcriptomics, or in other words, HTTR technologies, have really exploded. And there are both whole genome methods that really screen thousands of samples in one go for all the genes in the whole genome, basically, or more targeted approaches, which screen around 1,000 genes in thousands and thousands of samples. And so this is really, again, challenging, of course, the data analysis part. And I will try to make a point of how that's done. So I hope I'm still good with time. As I said, toxicogenomics comes with quite a few challenges. So if you look at high throughput screening, normally you have just one endpoint that you're measuring, or one molecular player that you're, like molecule that you're measuring, and you get a lot of data. But when you screen with toxicogenomics, you get 30,000 dose response genes. And you get, if you include 12 doses and you screen in many different cell types, and you include hundreds of nanomaterials, you will have enormous amounts of data to analyze and to handle also. So when it comes to toxicogenomics, there has been problems or challenges basically in terms of, well, first of all, study design, which has to be well done, as with any other type of experiment, of course. But also the challenge in terms of the technologies that are evolving. And these two combined have really caused issues and challenges in terms of reproducibility. And this is definitely true within the nanotox community, where different materials without proper physicochemical characterization and without proper annotating, so without proper persistent identifiers, for example, and I will get to this in a bit, means that it's very difficult to reproduce data. And on the toxicogenomics side, the reproducibility is difficult because you're measuring so much at once that if you look at just one gene in this whole mass of measured genes, the variability can be quite high, and you can't always rely on just one gene from a toxicogenomic experiment, which I think everyone nowadays is on board with. But so the focus has gone towards more focus on gene sets and gene networks and functional modules. And I will make a point of that in a while. And finally, the challenges also include, how do we present and how do we represent toxicogenomic data in decision making? And let's see if I manage to get you on board with this. So as I said, the focus has turned towards gene components or gene sets. And these can be comprised of, for example, a set of genes that we know are involved in a specific biological process. So inflammation, for example, cytokine activity, or some other process that we know is involved in toxicity. It can also be based on gene components that have been identified to associate with toxicity and to actually predict toxicity. And this slide here shows a tool that was developed by my colleagues, Pekka Kohonen. This says IMPRESS. This is actually published since a few years back, 2017. So please look it up. It's a tool that was developed basically by a crossover between transcriptomics data from chemicals in this case. But it doesn't, when you're on the biological level, it doesn't matter whether you're looking at chemicals or nanomaterials. What matters is what system you've used. But when it comes to genes involved in toxicity, they are most probably the same or similar. So this is then a tool that was developed by this crossover, or an integration of data from cell viability data from 59, the NCI 60, which includes 59 cell lines, screened for, I think, 100,000 compounds, crossed over with the connectivity map, which entails transcriptomics data for over 1,000 compounds. And this generated a so-called predictive toxicogenomics space, which comprises 14 gene sets or components, and altogether 1,331 genes, which are fit into these components in variable modes. Now, these 14 components, which relate to different types of toxicity pathways, can be used to currently predict liver injury in rats and in humans. It's been validated and it's described in this paper here. And it's currently being applied in the nano world for nanotoxicity and for lung toxicity in particular. And what we've seen in a very first screening is that it does cover actually much of what we see on the biological process or mechanism side for nanomaterials. This is a very early comparison to nanomaterial toxicity. But we are heading towards getting this validated for lung toxicity as well. So, so now the benefit of toxicogenomics is really that you can use this variable and highly dynamic data, which does cause challenges when it comes to reproducibility, but it has the potential and the strength or the weight of capturing dose dependency, and in particular these very sensitive changes to, biology adapts, and biology really, if you look at low doses and medium doses, which do have say acute phase response, but you normally then, if you're not exposed continuously, you would perhaps go back to a normal biological function if everything is okay and there's no other exposures. But in some cases, it actually leads to altered biological functions, which of course can lead to disease. And high doses, never mind, of course, often lead to disease. But distinguishing between these low doses that actually can also over time cause adaptive stress responses that either lead to go back to normal function or altered function, or actually then to adverse outcome. Toxicogenomics gives us the basis of distinguishing between these because it's so sensitive to capturing redundant biology. So because biology has a very well-established way of avoiding adverse outcome, we often miss the low dose responses that over time can lead to adverse outcome by just looking at endpoint specific toxicity. So now another, of course, turning a little bit the page towards adverse outcome pathways, which in terms of high throughput screening and toxicogenomics matter a lot, not only for development of adverse outcome pathways, which they do as well, but also for application of high throughput screening and toxicogenomics. So what you see here is an AOP for lung cancer initiated by nano-sized deposition and retention of nano-sized foreign matter. In this case, it's built based largely on data from diesel exhaust particles. And this AOP allows us to align different types of assays along the key events. So measurable key events that have assays applicable to nanomaterials along this whole AOP, which basically forms an integrated testing strategy. And so what you see here is some of these are actually high throughput assays that can be applied. In addition, of course, we do have, and some of these dig quite deep into the mechanisms of the steps towards lung cancer and the predictivity towards actually showing whether something has a potential of inducing lung cancer. But of course, we also have the high throughput screening systems, which can incorporate many of these in one go, and the toxicogenomic tools, which can cover much of this as a first tier testing system, where you then, after that, step into the more specific assays. So, okay, but coupled to this, and in order to really integrate toxicogenomics with adverse outcomes, we still have a challenge in the fact that we don't really know exactly which gene sets and which pathways matter in order to be as predictive as possible. And for that, we need linkage with much of the already existing information on genes and pathways in diverse life science databases. So toxicogenomics and analysis of toxicogenomics really relates to looking at the meaning of it all, and to incorporate information and data that we've gathered within science over the past several decades, where we have pathways which describe specific processes. We have ontologies that annotate genes in terms of both biological process, but also cellular positioning and molecular function. So all of this information is highly valuable to the adverse outcome pathways and vice versa, in order to link toxicogenomic results to adverse outcome pathways. So this is an example showing just how, keep going forward, how the AOP wiki, where adverse outcome pathways currently are stored and developed, how that wiki is mapped to molecular pathways, and how we can actually use this type of data to then inform toxicogenomic studies. And on the other hand, how the AOP wiki components can actually link into pathways that can be used in analysis of toxicogenomic data, so that you would have an actual direct link to the key events that matter. And by that way, getting first tier assessment of which key events are activated in a certain model system. So what we've done in relation to that is to develop this workflow where we actually go through a row of 6 steps in order to develop these bioinformatically employable pathways that link directly to the adverse outcome pathways in the AOP wiki. And that gives you a first step, first tier assessment of what could be involved in your study. And this looks like this. I put it here. It's not meant to be readable, but this is what the wiki pathway looks like for lung fibrosis. And this wiki pathway is linked to AOP173, which is the AOP for lung fibrosis, which is one of the most well-developed AOPs within nanotoxicology. And so what you can then, okay, so I was going backwards a bit, but this basically gives you an overview of how we can use AOPs in support of data integration of all this high throughput data and toxicogenomic data in order to actually apply this type of data in all stages of risk assessment, not only regulatory risk assessment, but also in safe by design strategies. So this is a bit of a complex picture. It was not meant really to be readable, but you can see the innovation process down here and different methods that we have positioned along the line of innovation. And what you see is that adverse outcome pathways really cover all of these steps where they support and guide data integration. And by having links to life science databases, you can also perform toxicogenomic experiments and link directly to adverse outcome pathways, which allows you to link to other types of data, if that makes sense. But of course, scaling and scoring is still an issue when it comes to toxicogenomic data, and especially in integration with other types of high throughput data. Okay, I'm running a little bit out of time, so I'm going to speed this up a bit. I'm going to skip this next slide, which was basically the same as the ToxPi slide that I was showing before. And I will skip that as well and go here, where you, so the final point that I want to make, and I've been talking about this first tier and next tier and integrated testing strategies, basically. So this is an overview of the tiered testing framework in the next generation blueprint for computational toxicology at the EPA in the US. And this is a new suggestion on how to screen in high throughput manner different types of substances. And we believe that it's highly applicable also to nanomaterials. Having in the back of our heads, of course, all the complexities and the requirements for nanomaterials that are specific in the model systems. But when it comes to the actual data and the outcome of that, the approach is similar. So what you have here up here at the top is an actual first tier broad coverage high content assays coupled to chemical or physicochemical structure. Of course, that still matters. I'm not saying that we throw that out. We need physicochemical characterization as much as we need biological characterization or bio interaction characterization. And you have, so you have the first tier basic cellular toxicity high throughput assays. You can also already have here high content assays for transcriptomics, for example, but in high throughput manner if possible and necessary. So, and you go forward then by integrating, by having predictive toxicogenomic tools that use this type of data and also the high throughput data, which are coupled to AOP linked pathway analysis. And this, of course, makes most sense for the bioinformaticians listening, but this is something that really matters. If you're able to do a bioinformatics analysis of toxicogenomics data, which is well designed and well done in line with nanomaterial recommendations, then you can have a AOP linked pathway analysis, which means that you get a first idea of what types of key events are involved in the potential toxicity. Now, then you go further to targeted high throughput assays, where you might look deeper into genotoxicity. There's a few high throughput screening assays for genotoxicity, COMET assay, and I think micronucleus is nowadays also available in a bit higher throughput settings. You might then go further. You might from this get an idea of whether there is or is not an AOP that gives you guidance on what to test next. So if you do have an AOP guided situation, you can do deepened testing based on that AOP, and it's driven or guided by the AOP. And then you deepen further into prioritized materials that you deepen the hazard characterization of using advanced model systems. And I'm thinking now 3D systems or co-cultures or other types of more advanced systems that are difficult to perform in high throughput. So I'm almost done. And of course, all of this is also useful to early risk assessment or pre-regulatory risk assessment and safe by design. So just a final point before my final slide. I have one more slide after this. All of this, because of the extensive amount of data, what really matters is to keep in mind that the data needs to be findable, accessible, interoperable, and reusable, so fair. And this is something that has become more and more clear with regards to nanotoxicology, where we've had a difficulty in actually integrating data. And that relates largely, not to mention also finding and accessing, but in particular, interoperable nanotoxicity data, because of the very multidisciplinary field where you have so many different types of data, and integrating this type of data requires interoperability on a machine readable level. And so we recently looked into how we can advance this also on the omics level, where in fact omics data within nanotoxicology, is currently detached from the rest of the data available, because it has not been applied to the same types of the same materials. The same types of materials, yes, but not the exact same nanoforms. So we've struggled with analyzing omics data within the field of nanotoxicology in line with other types of exposure and other types of studies. Okay, so final slide, just a pointer. Please have a look at the Sofia NanoSafe website. We have a lot of activities going on, and we talk a lot about safe and sustainable by design currently, and fair data. And there's information in English as well. And I have promised to provide some overviews on high throughput screening data and AOPs and omics. So please keep track of that. We have a LinkedIn profile if you're interested. Thank you to all my collaborators and all my funders. And thank you, Ulla.